Okay, so let's get started with a review from Jens, who's going to tell us about that topic which we've all been waiting to hear a review about, ML and Bayesian inference in cosmology, a very important topic with the launch of Euclid and all of that. So Jens, please go ahead. I'll give you a sign at 50-5.
Okay. Thanks, Henry, for this introduction, and thanks to the organizers for inviting me, and congratulations to the organizers for bringing together such an illustrious group of people, not only here in Paris, but also the experts in New York. That's very interesting. So what I want to do here right now is I want to give you an overview about Bayesian and machine learning approaches in modern cosmology, with particular emphasis to cosmic large-scale structure analyses, as this will be the next generation or the coming data sets that we will be working with. And in particular, this presentation is rather meant to be a rather informal, let's say, collection of thoughts and a discussion with you. So as a motivation, I want to bring up a rather suggestive plot, which I actually stole some intuition from by John Peacock. And this is basically a plot which shows the history of cosmic galaxy surveys over a century. So what you basically can... Sorry. Yeah. So basically what you can see here is the number of galaxies observed in surveys as a function of time over the last century till basically in the future where the big surveys are coming online. And basically what you can see here is that starting with actually Hubble's observation there, over time we have a tremendous increase in the observed galaxies in surveys. In surveys. The green curve here is photometrically observed galaxies. The red curve, that's spectroscopically observed galaxies. So receiving a spectra from galaxies much more expensive, even though they are more high quality distance estimators. We have fewer of them observed than just taking photographs of the sky and counting the galaxies over there. So what I want to make you aware of is that you are living at a very peculiar time, and at a time where cosmology is not longer data scarce, but will be dominated by data very soon. In particular, with the arrival of the next big surveys, Euclid has just been launched, and LSST is coming up there. So in terms of the absolute achievable goal, of course, we see a rising number of galaxies in our surveys, but if we wanted to get a rough goal, order of magnitude goal of what is potentially achievable, we can just have a look at the Hubble Ultra Deep Field, which was a deep drilling field in one direction, and just count how many galaxies have been there. That's not a super accurate thing, but you see that if you want to accept that as a benchmark, then we are close to reaching that benchmark, which is potentially close to the galaxies that are essentially observable. So within 1 century, we basically made a tremendous observational progress, and the data amount that we will be having is enormous. So, since we will not be any longer limited by the amount of data that will be available to us, we will be limited by our availability or ability to analyze the data. And that basically brings me then to how should we do this? Because one of the problems with cosmology is it's an observational science. So the phenomena we are interested in, they are in principle inaccessible to us, and we cannot directly manipulate them in order to map out causal relations very easily. And because also we observe phenomena at a tremendous distance, cosmological inferences are generally very uncertain. And in order to deal with that and distill out logically rigid and solid knowledge from that, we can basically rely on the Bayes inference device, which is basically just Bayes' law which provides us with a guaranteed logically and consistent knowledge update supported by the data. And if you want, you can interpret Bayes as one of the first machine learners, because this here is basically a mathematically formalized way of updating our knowledge given data. So that's actually all that we get from Bayes. And it's in principle very easy. Ben always refers to this as the mechanics of Bayesian statistics, because you just have to model it and fill it in with your data model, and then you just explore the corresponding parameter space of that. That is, in principle, set very easily, and in textbooks that can be done also very easily. But when I lecture, then the immediate question that I get from my students is, where does this likelihood come from? And even though we have guidance on how to update our logic or our knowledge logically consistent, the theory doesn't tell us anything about how the thing should be constructed. And in principle, we always rely on simplified assumptions on doing that, and that's one of the things which we will be discussing here today. So one of the things that I was interested in preparation of this talk is basically, why did Bayes actually become prominent in cosmology, and what were the reasonings, say, 20 years ago, 30 years ago, for it becoming dominant over the back then frequentist approach. And the arguments back then read very familiar. It's increased data sizes and complexity. New data sets were coming available. It is in algorithmic advances. Metropolis Hastings and Hamiltonian Monte Carlo techniques were becoming abundant that basically allowed the exploration of that. There was an increase of computational power, and Bayesian statistics was perceived to be very easy in modeling very complex statistical problems through the Bayesian hierarchical modeling. And finally, one of the things particular of interest to cosmologists and astronomers is that it comes with an explicit framework of marginalizing nuisance parameters in the theory. So I just had a look at that. That's the paper by Laredo, where he made a review basically back then asking why Bayesian statistics became prominent, and he made one of these plots where you basically count the numbers of papers published on arXiv with the title Bayesian in that, and he predicted that by the year 2016, all papers on the arXiv will be Bayesian. Let's jump to 2023 and let's see what happened. So why did deep learning become prominent in cosmology? And that's basically a review by Huertas and Company and Lanus in 2003. And if you look at the reasonings that are given there, they are the same. It's increased data sizes and complexity, algorithmic advances, it's backpropagation, CNN basically, increased computational power through GPUs, handling complex models through supervised learning, for instance, and nuisance parameters, as we will see, which we can just marginalize out directly in this framework. So we see that conceptually there's nothing new in there. So it is basically just a statement of that we are drifting along Moore's law of more and more computation. Algorithms become accessible to us, and therefore we can basically compute more complex problems. But what is conceptually very different now from, let's say, 30 years ago? And that is that machine learning is actually helping us to enhance the human data modeling. And what I mean by that is in Bayesian statistics, let's say the classical one, we had a lot of manual modeling. We had to set up these hierarchical Bayes models manually. We had to think about this, how to set them up. And with deep learning, there is now a chance that we can fully make this approach fully automatic and have feature learning, the relevant features in the data, fully data-driven approach. So that also means that the approach that we use to do cosmology is potentially moving from an algorithmic-centered approach where we code analysis frameworks to a data-driven approach where we basically try to provide the machines with adequate training data. So I think from my perspective, this is a fundamentally conceptually different thing. Other than that, these are the usual daily problems that we have as researchers when dealing with data. And you can see here also at this plot is roughly in 2017, deep learning took off. That's actually very well related to the fact that back then the convolutional networks became first sufficiently powerful to surpass human capabilities in classifying. So you see that this is very powerful technology, in particular for an observational, optical observational era we are in. So what is the goal that we want to achieve? And here's my one slide on cosmology. And this encapsulates everything that I think is cosmology. It's based on the Einstein equations here, closed by the Bianchi identity. And basically, this is everything we want to sort out. This is our world model of the universe. And from that, we can derive the theory framework from which we can derive any specific hypotheses that we can test against the data. You can read off immediately the questions we want to answer. That is, what is gravity? What are the sources of gravity? So what's the energy momentum tensor? And because we want to make predictions that are testable against observations, we need to ask the question, what are the corresponding initial conditions? Because if we had them, we plug them into our second-order differential equations and make predictions for how the universe works. So that's a rather theorist perspective on that. If we are from a Bayesian perspective, we would construct such a model. We would basically construct, this is a posterior distribution of the universe. The initial conditions is a 3D cube of white noise fluctuations, and we have our physics parameters here. They are fed in, and they are creating initial conditions which are then evaluated with some kind of structure formation model to yield our present-day large-scale structure. And then we have other models on top of that that account for galaxy formation, baryonic physics, and so on, selection effects, biases that turn that model prediction into an observable prediction that can be compared with the actual observations. And you can basically think of that in this approach, we can just write the conditional probabilities for this approach, and from that, we can just directly model our Bayes theorem and perform the protocol, which is just explore the corresponding parameter space. So this is certainly the high goal. According to our understanding right now, if we had access to this information, we basically have everything we need to understand about the universe. This is typically a very high-dimensional problem and cannot solve very easily, and we talk about this a little bit later here. So just to make sure, this is certainly a cartoon and an outrageous understatement of the actual complexity of this problem and an understatement about the work that everyone is doing and in detail. And just to give you a feeling for the actual complexity that we need to address, these are just the intermediate steps of the forward modeling, starting out from the initial conditions, the evolved density field, then we need to create galaxy fields on top, we need to move the things along the light cone, accounting for all the cosmology in there, redshift distortions, then we have to model the instrumental effects and come to the observations. And only after that pipeline, we can actually compare with significance to the actual data and hope that everything worked out very nicely and fine. The problem with that is that this is a very ambitious program, and it's not, at the moment, I think, not entirely clear of how to optimally extract information from the data. Should we take the entire field, so reconstruct the entire three-dimensional initial conditions, as would ultimately be the goal? Or can we get away for certain questions that we would like to answer with simpler, less high-dimensional summary statistics? And this is a very simple exploration done by Florent Leclerc and Alan Havens. And they just wanted to see in a very simplified framework the comparison of the three basic approaches that we have. This is a standard likelihood-based analysis based on the two-point correlation function or the power spectrum. Then we compare it also with simulation-based inference, which is likelihood-free inference, or previously known as approximate Bayesian computation. It's all also based on the two-point correlation function, and then we basically try to investigate what happens if we do this at the full field level. The corresponding Bayesian hierarchical model is just shown here, and you can see that you can interface that model at the different levels of complexity. And I just want to jump into the conclusions here. If you compare those different statistics on simulated data in this very simplified approach, then you see the green contours, they are the simple standard likelihood-based analysis. The bluish contours, they are the two-point correlation-based simulation based inferences. And then the yellowish contours, they are the full field level inference. That basically shows that already in this simplified case, the field level approach, by trying to model the entire field, you leverage additional data constraints than from simple summary statistics, or vice versa. The summary statistics are not necessarily fully informative and maybe not optimal for the extraction of information, and we'll discuss this a little bit later. So the high goal, the ultimate goal that we would like to have, is to perform field level inference for cosmic structure surveys, but this is also numerically super challenging and requires a lot of computation. But let's just have a look at that. So field level inference in cosmology is absolutely nothing new. It has been around quite some time, and in particular, I'd say it started with the CMB, maybe even earlier, but I'll start with the CMB, where the task was to basically analyze the temperature fluctuations on the sky and measure power spectra. And in particular, since the CMB is almost Gaussian, we can just use linear data modeling. There's the early universe, everything is linear, and to a very high degree of accuracy, we can assume it's Gaussian statistics, and then we can just write the vena posterior here, which is just a Gaussian likelihood with a Gaussian prior, and then I think the audience is well informed that then the vena filtering and Gibbs sampling approaches have been developed for CMB analysis, and you can see, for instance, one of these examples here. This is a vena filtered map. We have the masked region in the galaxy. You see that the vena filter is still capable of extrapolating large-scale information here, but the Gibbs sampling approach is then sampling random fluctuations in these regions and combining the fluctuations field with the mean field gives you a full field of the CMB. So if you want, this is a very simple generative model for CMB, entirely Gaussian. And that was the motivation also initially to transfer that kind of technology to the cosmic large-scale structure community. Apparently, this seems to be the case that communities which have the best data first develop these technologies, and then it's moved on to the next. Now, large-scale structure is becoming more data-dominated. But we are also switching to machine learning, so we hopefully can feed back something. But I just want to show you the problem that happens with that. So if you naively apply this to cosmic large-scale structure surveys, then this is not representative for the actual statistics that you're dealing with, and also not for the signal you're dealing with. So if you just look here at these two panels, this is the ensemble mean field of a 2M++ galaxy compilation. It's an actual galaxy survey, basically vena filtered. And below here, you see the corresponding standard deviation or variance map. And first of all, what you see is that all these structures are quite roundish and blobbish. The vena filter, because it's Gaussian, cannot account for higher order statistics. It's just isotropic power spectrum that basically introduces these spherical things. And the other important thing is because if we're looking into analyzing statistics, then we always look into the tails of distributions. If you look here at the variance, it has absolutely it's flat. It has no information about the signal. And we know for a Poisson distribution, the variance should be dependent on the signal. So there's something off in the modeling. The next approaches then that were explored is log-normal modeling that was supposed to be better in capturing the one-point nonlinear distributions. And that is the middle panel here. So what you see first of all is you still have these roundish features here because also the log-normal is not accounting for higher order statistics. It's just for the isotropic power spectrum in there. But you start seeing, because it's a nonlinear model, you start seeing that the variance now is actually capturing information of the actual signal. So this looks much, much better. But experimenting with that was still not very sufficient because obviously we do not get this filamentary structure, right? And that's why in around 2013, a lot of people started experimenting actually with physics-based modeling approaches where you don't try to use simple statistical formulations anymore, but you just try to simulate it out. And just here to show you that is an LPT model, and you really see nicely the filamentary structures here, and you also see that this kind of modeling is actually taking into account much, much more the statistics of the actual field. So from that moment on, I think it became more and more apparent that for the large-scale structure in particular, if you want to do detailed analyses, we have to do more than the standard textbooks approaches, and that it's potentially a computational approach. So in particular, I will pick out our own code here, but there are other approaches here which you should explore as well. This is basically, we did ab initio modeling of the cosmic large-scale structure. So we set up this Bayesian hierarchical model. We have the Gaussian initial conditions. They are fed into, this is white noise initial conditions. They are multiplied or convolved with a power spectrum, fed into a structure formation model, and then we predict data, also giving some galaxy biasing model. And you can see that the cosmological parameters enter at all the stages. It's the initial power spectrum, it's the structure growth, it's expansion dynamics of the universe. So the model can account for various structure formation models like LPT, PM, and COLA, but you have to make explicit assumptions on the likelihood, like Poisson distributions and so on. Yeah? The problem is very high dimensional because we infer the entire field, so we have 10 to the 6 to 10 to the 9 parameters in the inference approach. But and the technology that actually enabled that is the Hamiltonian Monte Carlo technique that basically used backpropagation techniques through this entire model, which made the exploration very efficient, and the development of differentiable structure formation models. And this has been continued till today. So just to give you an idea of what you can expect from that, that's an application of this kind of Bayesian analysis to the actual data of the 2M++. This is data surrounding us. We are in the center here. This is a recovered ensemble mean. This is a variance map, so you see the uncertainty. This is a signal-to-noise map, and if you now look into this fluctuations map in regions where we have high signal-to-noise, you see we recover the large-scale structure nicely, but in regions where we do not have high signal-to-noise, it explores large-scale structure, and consistently you can see that it really uses the physics extrapolation to connect filaments. And all these structures are plausible under the data model and the data. So here's the reconstructed initial conditions, and just to show you and convince you that this is the proto-structures of the actual meta-distribution in the universe, I just flip it. That's how the large-scale structure looks today. Red dots are the actual galaxies, and I just flip back and forth, and you can convince yourself that these structures are actually corresponding. Since we fit an entire physics model, we get all kinds of derived quantities, including velocity fields, and if you're doing transient analyses these days and use the GLADE Plus survey, then you potentially use our velocity fields for these analyses. But let me move on to actually doing cosmological inferences with this kind of field level approaches. That's the work by Natalia Porkeris, who actually built up a very complex model for cosmic shear inference. I don't want to go into the details of that. I just want to show you the final results. So if you do this, of course, you get the recovered field. This is the ensemble mean, and that's the ground truth, so you see they correspond. But now let's have a look just at the inferences of the cosmological parameters. Blue is Natalia's result, and the orange ones, they are comparison with the standard angular power spectrum analyses. And you see two things. First of all, the constraining power is higher if you use the entire field, and you also break parameter degeneracies. So lifting parameters is potentially possible because the model jointly uses matter power spectrum, the geometry, expansion geometry, the tidal field, structure growth, and distance redshift relations. It's all built in the model. You don't have to think much about this, but it jointly uses these physics to constrain the parameters. So these kinds of models, of course, because they are Bayesian hierarchical models, require a lot of physics development and model. So if you want to go beyond that and don't want to have a explicit modeling for your likelihood, then recently there has been proposed you can use diffusion networks, and you just need to have training data, and you basically add noise to your training data until it's completely noisy, and then you basically train a network to denoise it, and then you can basically just have random fluctuations in the latent Gaussian space, and then generate arbitrarily many realizations without having to worry much about constructing the actual data distribution. And that's a project here by Ronan Leguin, who basically implemented this diffusion network as a conditional diffusion network for this kind of three-dimensional inferences. Here you see the ground truth, that's the recovered field. You see the power spectra are recovered very nicely. And what you can see here is a cross-correlation with the ground truth for Ronan's model and the results that you would get with a very simple Wiener filtering. So you see that it's already better. So the impressive part here is that basically you do not need to construct explicitly a likelihood framework. It also does not require gradients of the likelihood and the model, so it can be just trained in a fully data-driven approach. And I also would like to point out that recently there has been another approach to do this initial conditions inferences with machine learning approaches, which you might want to explore as well. So if we do not want to do this full field inferences, but we want to maybe do cosmology for the impatient, then we can do implicit likelihood inferences, where we basically try to project the data first into a lower dimensionality and then analyze it. So the idea of implicit likelihood is that if we cannot explicitly formulate the likelihood, then the likelihood is implicitly defined by a simulator. You just draw your model parameters from the prior, run your physics simulator, and then you basically generate artificial data. And that data is then correctly generated according to your likelihood. Yeah? So these pairs, X and D, they are basically drawn from the joint distribution, and that basically allows you very easily then to construct the posterior distribution through a data-driven approach. So you can just model the posterior distribution by a parametric conditional distribution like this Q function here, and then you try to match Q to the actual distribution by just optimizing Kullback-Leibler distribution through this approach. In the very simplest approach, you could just assume that it's your Q distribution is a Gaussian, and you just fit the mean and the variance with a with neural networks, which would then adjust and compress the data to the space in which you want to infer. But more general than that, you could use normalizing flow or mixture density networks. Mixtures of Gaussian distributions are typically used and are very sufficient to do this kind of work. So the steps of simulation-based inference are then as follows. you would create a training set. This actually may include some data compression. What you call data eventually, that's your own choice. And then you define a parametric model, and then you optimize the parameters of this model by maximizing the loss function, basically like that. And then you can perform an inference, and basically you can then just feed in any kind of large-scale structure into these first pre-trained compression algorithm, and then that will be fed into the distribution, and then your inference basically returns a distribution which you can then use for your inferences. And while for this compression of data into a smaller dimensional data vector, you can use everything like a convolutional neural network or whatever you want. It is not necessarily guaranteed that this kind of data compression is information optimal, and that's why there has been work by Alsing, Charnock, and Makinen on trying to basically develop the optimal data compression in terms of under some information criterion. And the idea here basically is that you take your input data, you run it through convolutional layers into some smaller dimensional latent space, and then you get these parameters out, and you just estimate the Fisher metrics of that. So you measure basically the score or the response of the likelihood with respect to your parameters, and you basically train this network such that it optimizes the Fisher information. So under some mild conditions, you can basically then demonstrate that it is Fisher optimal in information retrieval around this point here. And what you can do in practice is you can use these kinds of summary statistics to train then, feed that into your mixture density network or other approximating distribution, and map out and learn the distribution. To do that, there is I also suggest there's earlier works on this kind of optimal data compression by Alan Havens, and a recent one paper based on unsupervised learning data compression that you can use also. It doesn't matter so much what kind of summary statistics you use, as long as you apply the same summary statistics to the actual data and the simulation data. You don't make a mistake. You may just not be optimal. So just to show you an application of that, that's a work by Lin et al., where they basically tried to apply simulation-based inference and compare this to MCMC in case of the cosmic shear with KITS data. And they applied basically exactly this training procedure to this, and they recover the 12-dimensional posterior distribution. Should say that in this case they focus mostly on two-point correlation functions as statistical summaries, so they can easily compare with the standard MCMC approach. And if you look at that, then you see that the standard MCMC and the simulation-based inference give very similar results. And the simulation-based inference just required on the order of 1,000 simulations. So this is very encouraging, and certainly a case that simulation-based inference can be very competitive to MCMC. So one of the things that we need to do in order to infer the initial conditions or any physical quantity is we need to quickly explore the high-dimensional parameter space. And that requires us to have fast simulators. An additional problem is that we also need to have very accurate simulators. And I want to show you here is another problem where handcrafted feature selection in the data becomes problematic. So what you see here is a selection of mass estimates for clusters, for actual clusters in the nearby universe, measured with different probes. And all these mass estimates are quite discrepant with each other. And the other thing is also, according to the steepness of the mass function, a small number of high mass object would basically rule out lambda CDM. And if you would take that here serious, that would be sufficient to rule out lambda CDM. But according to the scatter in here, I think it's not very trustworthy that this is the case. And the problem is, if we look into the nearby universe, we are so specific that we are cosmic variance dominated. The characteristics of each individual object really is relevant, and the significance of high mass objects in such a volume is significant, because even though they contribute the smallest fraction to the volume, they have a significant impact on the cosmology. And I just want to show you, these are the mug shots of some of these clusters in the nearby universe, and you see the specific intricate details, the complex cosmic environments, and you can easily realize that you certainly cannot make simplifying assumptions like sphericity or the virial theorem might not apply in this case. So this requires very accurate modeling and nonlinear structure formation. It needs to be fast and scalable too. And here, that's the reason why in the past lots of people developed approximate large-scale structure formation models. It's Lagrangian Eulerian perturbation. There have been works on adhesion models, all kinds of approximate models, effective field theory. If you just want to look into this plot here, this is a corresponding n-body simulation run with the same initial conditions as all the other models. And then you just look into the middle panel. This is the Zeldovich approximation. That's the second order, and that's the third order of this. And you can see that it is quite different, right? You see overall it's correct, but in detail it's not matching. So then there has been a quite interesting technique developed by Svetlin Tasev. I call this residual correction technique. It's COLA, it's co-moving Lagrangian acceleration. And the idea here is that you can decompose your equation of motion into a part which you can model through linear perturbation and a residual component also in the forces. And then you can solve that equation of motion. And if you do this, you only need 10 or 20 time steps to arrive at a field that looks like that. So this looks significantly better than the 3-point statistics for the LPT. And due to the n-log n scaling of the algorithm, it is also potentially faster than evaluating higher order statistics in the perturbation theory. So compared to that, it's something like 100 times faster than n-body. And that has been a significant advancement. But still, in order to match masses with that, we have to calibrate things and see if they are sufficient for the accuracy that the data has. That's basically what we did here. That's a work by Steven Stopira. And he basically compared typical particle mesh with COLA. And you see that COLA, first of all, has a very nice convergence towards the gray region. And you can see that the green curve, that's the typical particle mesh code, which does not necessarily nicely converge. And that's because the particle mesh code not necessarily conserves the large-scale integration, and that can have an effect on that. But with about 20 to 40 time steps, that is sufficient to get the cluster masses right. If you need more accuracy, you might have to do more. And that's exactly then where the first time machine learning came to the rescue, I think, or is coming to the rescue at the moment. In here at 2019, they basically proposed to do this residual correction step not by updating the differences in the equation of motion, but by just training a neural network, a VNet, that basically translates between the Lagrangian LPT model and the finer resolved n-body simulations. And this is a simple VNet structure. It can encode cosmology as a style parameter in there. It is fully differentiable, and it's very accurate and fast in this. So if you look into detail, here's a comparison of this model. You should look at the emulator curve, and you should compare it to the yellow and green curve, which are the COLA runs, which to date are the most accurate ones that we are using. They deviate already here right now, whereas you see that the emulator at a scale of k equals 1-ish is still very good. The more important thing is you also want to have higher order statistics correct. And if you look at the bispectrum, you see that the bispectrum, for instance, is not reproduced very well with COLA, but is very well reproduced with the emulator. So you see that it's added accuracy on top of that. So you can even look much, much more into detail if the halo mass functions are accurately recovered. And then if you look at standard friends of friends, all models agree. At M100C, you see that you start having deviations at the smaller scales, but you see at the M200C, the emulator is on par with the n-body simulation. And if you want to think, basically this here are different mass estimates at different radii. Basically, it's probing the mass profile of the halos to some extent. So you see that it's significantly outperforming our previous approaches. And because it's differentiable, you can just nicely fit it into any method. And you can just pipe it into any pipeline, add it in here, and just differentiate through this. There's absolutely no problem with this. So it's remarkable and beautiful to integrate this. And just to show your first application, Ludwig on Tuesday talked a little bit about this. But if you do a full Bayesian analysis with this network in there, then you see that it's actually working. And this is the ground truth here. And these are the fine details that are worked out after some details. So you see that it's actually working, and it has now much higher fidelity in reconstructing the initial and nonlinear density fields. So one of the actually absolute biggest bottlenecks in cosmology is the galaxy bias. Everything we talked so far is actually the easy part. So the dark matter simulator is the easy part. The last mile of connecting that to actual data is super challenging, and I'd say it's not really a solved problem at the scales k equals 1-ish, which we would like to address. And that's certainly a community effort that has to be done there, and certain things. You see that there are also certain requirements for different methods. You might have differentiability requirements and so on. A simple approach that you could, not simple approach actually, but you could just try to translate dark matter fields in n-body simulations to hydro fields and translate between the dark matter and the galaxy fields in there. That was work by Sang et al. And they basically use convolutional networks to deterministically translate dark matter-only fields into galaxy fields. And they had to do this in a two-step learning process because the actual data is zero inflated. If you have a sufficiently high resolution, most of the volume is not filled by galaxies. And if you just want to train a model that makes a prediction, it will very likely just bet and say there's no galaxy everywhere. So one has to first, in a two-step, one creates a mask, which just makes a probability of where a galaxy could be. And then after that, you train another model that predicts the number of galaxies there just for these points. Otherwise, it is very challenging to train it. But independent of that, you see that the prediction of that model goes to very high k, up to 10. Of course, it's fixed to the specific cosmology, but in principle, sorry, to this particular model, but in principle, this shows that there are ways forward. Another approach that is more in line with correcting the residuals, that's work by Dai and Seljuk. And they basically thought about various ways of correcting the displacements in actually fast PM simulations. And they basically constructed a very simple model that is living in Fourier space. It's basically a convolution kernel in Fourier space with a nonlinear response function that can be density dependent or dependent on various fields in the simulation. And you can basically then train it to translate the displacements from dark matter simulations into something that looks like a star density. They call this Lagrangian deep learning. So the upper panels are the predictions from the Lagrangian deep learning model, and the lower ones are the corresponding ground truths in the TNG simulations. And you see there's really great correspondences between this. And if you look at the power spectrum, for instance, for the star density, then you see that it's quite okay at k equals 1-ish. And so this is a significant achievement, in particular, since we only have on the order of 10 parameters in there. So in terms of machine learning, this is quite interesting, because one can think about putting such an approach into the machine learning itself. So I just want to show you another approach where we can bypass the requirement for enormous data sets. That's the neural physical engine, and this idea here that you encode physical symmetries like translation variance, local rotation invariance, and locality directly onto your network. And basically, the goal is that you translate your density field ultimately into a conditional halo mass function, and then you generate from that a full density field again. So the symmetries that you can encode into this convolutional network, they are the symmetries like that. And if you constrain the neural network or the convolutional network to only have these symmetries, then you are left with 17 parameters. And that's quite remarkable. So 17 parameters is something that you can actually learn on the fly while you do your Bayesian inference. You don't need to pre-train it. So it is an example of zero-shot learning that you can do. And in fact, just to show you the application, I just want to play this video here. So what you see here is that model was put into a initial conditions inference. What you see here, this is the nonlinear meta reconstruction. This is the ground truth data, and here the model tries to basically, this is a posterior prediction for the actual halo field, and you now see that as the learning process progresses, it's actually working out, it's matching the actual data, and up here you see that it's simultaneously trying to match the conditional halo mass functions and working it out. So you can see that this kind of approaches are working, and you could potentially just try to learn those things from the data directly. So these are by having physics-informed networks. This could be a very interesting approach forward. So one of the things that is, of course, what we have in there is that machine learning is certainly necessary to surpass the human modeling that we had. You saw that basically machine learning, these approaches are always used to enhance the human modeling where we can't do this. But then, of course, it is some kind of black box. And because of that, I think a relevant piece of technology that needs to be developed for this era is to basically technology that helps us understand. And we had this discussion on Tuesday, and I don't want to talk much about this, but I just want to focus your attention again on Luisa's work, which I find is one example of where you can try to make sense of a trained network, and that was discussed on Tuesday, actually, where you basically compress your signal into a latent space such that the latent space is as orthogonal as possible, so that the individual variables in there are not correlated, or at least as least correlated as possible. Then you have a query, and you have a decoder network, which in this case now is supposed to learn the halo profile. And the idea here is that you basically, by compressing this to the essential latent space, if you had a sufficiently large latent space, then you would capture all the relevant physics information that is relevant to determine this. And Luisa basically also then did this analysis through mutual information between these parameters at different distances to figure out how these latent parameters are basically influencing the outcome of this network, and that's basically what you can see here, that they basically have very distinct predictions. So you need 2D to accurately model the profile up to the virial radius. You need 3 latent space features in order to describe the profiles beyond the virial radius. And if you have 4 or more, then you can also start seeing impacts of infalling material in the outer profiles and splashback boundaries. And this is, I think, a very nice idea and conceptual framework to interrogate machine learning. Another thing that we can use is we can use machines actually to help us learn about the universe. And this is a project by Andrea Kostic, who was basically interested in asking the question, given everything we know about the universe, if you have our posterior, so where do we have to look in order to find something new? And this is a conceptual work where basically given some inferred initial conditions, you have some parameter of interest here. You then work out the Fisher information, and we call this thing here the parameter sensitivity, but you can just do this, and you can basically do this for every position in the space, so you could make a map of the Fisher information. If you look then for, say, typical cosmological parameters, these are the sensitivity maps that you get, so these are the gradients, but if you're then interested in the Fisher information, then you get a map of the Fisher information which would inform you where you should look in order to learn something more about these parameters. And this is an example where you should look. It's quite inhomogeneous about the sky. Right now we scan everything with the survey, so that's not of such interest for cosmological parameters. But if you had a very specific question, then one could ask for a very targeted survey and ask where is my chance highest to retrieve the decisive information. And that's basically it. So I come to my summary and conclusion. So the cosmological data from now on will no longer be scarce. And I think the only thing that will limit our knowledge gain is our capability of robustly analyzing that data. So the inference technology could be field-level inference, which is the ultimate goal of really having the posterior distribution of the universe, including the physics parameters and the initial condition. It is information optimal because it tries to achieve to extract everything that we can potentially get from the data. It is a complete characterization of the data without any compression. But if you want to make progress on specific questions, then the implicit likelihood inference approach might be the best choice for you. That's a simulation-based inference approach, which does not require explicit likelihood modeling. It can have information optimal data compression geared towards answering the questions that you have, and it's a viable alternative to classical MCMC. So the machine learning is an enhanced data modeling. It allows us for fast physics emulators, but also automatic feature design and help us to design likelihoods and so on. But the current limitations, to my understanding, is definitely handling small-scale baryonic physics and galaxy biasing in there. And the biggest bottleneck to make progress there is the training data, the requirements, which are the accuracy, size, the diversity and representativeness for the actual observed data. Thank you.
Thank you very much, Jens. Are there some comments and questions? So right there, please state your name for the people on Zoom. This guy here, what's your name and where are you from?
Guillermo.
From
Amsterdam.
Okay.
Thanks for the very nice talk. So I've seen that when doing field-level inference, people either try to reconstruct the initial conditions, but in that case they fix the cosmological parameters, or they try to reconstruct the cosmological parameters, but in that case they fix the initial conditions. So what makes so difficult, or why haven't we been able to reconstruct all, like the high-dimensional initial conditions and the cosmological parameters simultaneously?
The answer is multifaceted. First of all, it's a super challenging problem. We are talking about a million-dimensional plus X parameter space. And while the inference of the initial conditions is more like an image reconstruction problem, you have millions of parameters which are very similar. The cosmological parameters on that are very challenging, different. So from a technical point of view, you can imagine this. You have this concrete block of the initial conditions, and then your cosmological parameters, they make up this very thin banana. And with the HMC, you have to move this concrete block along these bananas, and it is just going everywhere. Think of gravity in a million dimensions. The forces are extreme. The curvature of that is just a big challenge to get this joint parameter space under control. That's one thing. The other thing is the actual modeling. So Halo-Bayes modeling such that it's differentiable and accurate enough to do this. This is one of the biggest problems that you do this. If you would do just dark matter only, the problem is much less than that. That's also why Natalia Porkeris is, for instance, doing this with weak lensing. These issues are less there. They are not gone, they are less. There's a more direct connection to the dark matter through the gravitational potential. And she's doing this. She's jointly inferring the initial conditions and the cosmological parameters. So here's an example where it actually works.
Okay, are there some more comments? There's Florent Leclerc. I think I know what he's going to say.
No, you don't.
Okay.
This is Florent Leclerc from IAP Paris. Jens, so we've known each other for a while, and one of the points that I often hear you make is that Bayesian hierarchical models, the old flavor without neural networks, give us a way to do causal inference. That is to say, not only learning correlations in the data, but having a feeling about causality. And I was a little bit surprised that you didn't talk about that today, and I was wondering what your perspective is on keeping a causal understanding of what's happening in a world where we have neural networks, in particular to this problem of galaxy biasing that you mentioned.
Yeah, I know what Florent is referring to. Just I make this joke frequently.
You put bias under the rug again?
So it's basically this. This is a generative machine learning model, right? But that's definitely not how nature makes dogs. Yeah? So that's basically it. It's a difference between an associative model that is just looking for correlations and is recreating something, and the actual physical process in nature that's generating it. So that is, of course, why we have the physics model in there. But I think my answer to that, Florent, is right now is after we have done the exploration with a machine learning algorithm, we can still put it into a causal model. We can still put it again into an n-body simulation, which would then give us causal reasoning. So causal reasoning for an observational science is also non-trivial, because in order to do causal inferences, you need to actually run experiments at some point. And that's why in cosmology, we can't just do limited causal experiments, because we can't just work out associations. So yes, it is there. It is a frequent statement that I make, you're right. And I think as physicists, we are interested in not working out the correlations, but the causations, and in particular when we reconstruct the initial conditions of the universe.
Thank you. Are there some other questions or comments? Louisa.
Hi, Jens. Really nice talk. So in the field level inference, what happens with like unknown unknowns? You know, because you can, if I understand correctly, right, you can model in the forward model in the systematics and everything. But what happens, like, do you have a way of seeing whether you miss the systematic or? Yeah,
so there's one work also by Natalia Porkeris, during her PhD, where we try to answer these questions of unknown unknowns. And we can actually formulate it in a Bayesian framework. In this particular case, we basically looked at the foreground contamination. We didn't know what this foreground contamination is, but we knew it is on the sky somehow. And we basically set a helpix map up with parameterized by pixels, which could assume any kind of value. And the nice thing is that for that particular case, we were able to marginalize out these values. So we didn't have to sample them explicitly. But what it is bringing is bringing a robustness to this kind of foreground contaminations. And what I also have not shown here is the nice thing is then that a posteriori, your model can inform you that here in the data is something that I did not like, that is conflicting with the physics information you have provided me with, and I can make maps, a posteriori maps, which basically inform you where in the data it did not like something. And then you can follow up and check. Sometimes you see it's certainly of technological signature if it's just a stripe or something like that. Then it's evident, but it adds to the robustness that it informs you about something that it didn't like, and then you can follow up and investigate. So rather than just discarding it as nuisance, you could just check it, maybe it's physics, but it informs you about, and very specifically, it tells you that part in the sky is what I didn't like. So it is not just a rather uninformative information that you get, but it's very informative. And we are exploring these kinds of ideas more. Yeah.
Very nice, thanks.
Okay, thanks. I think we have time for one more quick question or comment. I didn't see anything on Slack. Are there any other comments? Okay, well, I think it's lunchtime then. Thank you very much, Jens, and all the speakers. Well, Miles as well.